On a server farm tonight, a machine is doing something that would have seemed like sorcery to almost every human being who has ever lived. It reads a sentence you just typed, understands what you meant, and writes something new in return. It looks at a blank canvas and paints a face that has never existed. It scans millions of lines of text in the time it takes you to blink, all of it running on instructions written in ones and zeros. Now picture a different scene. A merchant in an ancient marketplace, cross-legged on a woven mat, sliding small wooden beads across a frame to keep track of how many sacks of grain he sold that day. Between those two images lies one of the strangest journeys in human history, and the question it forces us to ask is deceptively simple. How did we get from beads on a string to machines that can think alongside us? Not machines that calculate, not machines that store, machines that write, recognize, generate, converse. The answer is not a single invention. It is a chain, an unbroken chain of small, stubborn attempts by ordinary humans to extend the limits of their own minds. Follow that chain far enough and you end up here in the age of artificial intelligence. But to understand where we are, we have to go back to where it started, not in a laboratory, not with electricity, with beads. Long before anyone imagined a machine that could think, humans faced a much older problem. They needed to count and their fingers were not enough. As civilizations grew more complex, the numbers involved in daily life grew with them. Farmers needed to track harvests across entire seasons. Traders needed to calculate prices across currencies. Tax collectors needed to record what was owed by entire villages. Builders needed measurements precise enough to keep a temple standing for centuries. Astronomers needed to track the movement of stars across years, not days. Human memory alone could not hold all of that. So, across different regions of the ancient world, people began building tools to help them count. Among the most enduring was the abacus, a simple frame holding rows of beads, each row representing a different value. There is something almost humbling about the abacus. No gears, no electricity, no circuitry, nothing more than beads and a frame. And yet, in skilled hands, it could perform addition, subtraction, multiplication, and division faster than most people could manage on paper. For thousands of years, in markets and counting houses across the world, this simple device was the fastest calculating technology available to humanity. This is where the story of computer evolution actually begins, not with silicon, not with electricity, but with the very human desire to calculate faster and more reliably than the mind could manage alone. But the abacus had a limitation baked into its design. It was only as accurate as the person operating it, and it had no way of catching a mistake. It simply reflected back whatever the human told it to. And that limitation would eventually push people to imagine something stranger. What if the machine itself could do the arithmetic, without a human hand guiding every movement? By the 17th century, that question had become an obsession for a handful of inventors across Europe. One of them was a French mathematician named Blaise Pascal. As a teenager, Pascal watched his father struggle through the tedious, error-prone work of tax calculations, and he set out to build something that could do the job automatically. The result, known as the Pascaline, used interlocking gears and dials to add and subtract numbers mechanically. Turn a dial, and the gears beneath it would shift, carry values from one column to the next, and produce a result, without the operator performing the arithmetic in their head. It was slow by modern standards and limited in what it could actually do, but it proved something enormous. A machine built from gears and metal could replicate a mental process. Numbers were no longer something that existed only in the mind. They could be represented mechanically, moved mechanically, calculated mechanically. Other inventors across Europe pursued similar ideas in the decades that followed, pushing mechanical calculation toward more practical devices. Slowly, an idea took hold that would define the next several centuries of computing. If arithmetic could be mechanized, what else could be? That question would soon fall into the hands of a brilliant, restless English mathematician, a man who would imagine something so far ahead of his time that it would take more than a century for the rest of the world to catch up. Charles Babbage did not set out to invent the computer. He set out to eliminate a problem that infuriated him: human error. In the early 19th century, complex mathematical tables used for navigation, engineering, and science were calculated by hand and then set in print by human workers. Both steps were riddled with mistakes. A single miscalculation, repeated across a printed table, could send a ship off course. Babbage believed the solution was to remove human fallibility from the process entirely. His first attempt was the difference engine, a mechanical calculator designed to compute mathematical tables automatically, using a method that avoided the kind of errors humans routinely made. It was an extraordinarily ambitious design for its time, built from thousands of precision-machined parts. Funding and manufacturing limitations meant Babbage never completed it in his lifetime, but the underlying engineering held up. Then Babbage did something far more radical. He began designing a machine that wasn't limited to one specific calculation. He called it the Analytical engine, and in it, you can already see the outline of the modern computer, nearly 100 years before one would actually be built. The Analytical engine was designed with a section that took in data and instructions, a section that performed the calculations, a section that stored numbers for later use, and a section that produced the results, in modern terms, input, processing, memory, and output, the same structure every computer still uses today. Crucially, it was designed to be programmable. Feed it different instructions, using punched cards borrowed from an entirely different industry, and it could perform different tasks. Working alongside Babbage was Ada Lovelace, a mathematician who understood the implications of his design more deeply than almost anyone else alive at the time. In her extensive notes on the Analytical engine, she described how the machine could be instructed to calculate a complex sequence of numbers, a sequence of steps widely regarded today as the first algorithm ever written specifically for a machine to execute. She also saw further than Babbage in one respect. She recognized that a machine manipulating symbols according to rules might eventually go beyond pure numbers, into music, text, or any information that could be represented symbolically. None of it was fully built. The Analytical engine remained, in large part, an idea on paper, brilliant, but a century ahead of the technology needed to construct it. And that is precisely why this chapter matters. The concept of a programmable machine, one that could be instructed to do many things rather than just one, existed decades before anyone had the tools to make it real. Somewhere, a machine had been imagined that could follow instructions. Now humanity needed a way to actually feed those instructions in. The answer had already been invented, just not for computing. In the early 1800s, a French weaver named Joseph-Marie Jacquard built a loom that could weave complex patterns automatically, guided by a chain of punched cards. Each card carried a pattern of holes, and each hole corresponded to a specific action the loom should take. Change the cards, and the loom would weave an entirely different design. It was, in essence, a machine being programmed, just for textiles rather than mathematics. Decades later, an American engineer named Herman Hollerith borrowed that same idea and pointed it at one of the most overwhelming data problems of his era: the United States Census. Counting and cross-referencing the population by hand had become so slow that officials feared one census would barely be finished before the next began. Hollerith designed a system where information about each person could be recorded as patterns of punched holes on cards, then read and tabulated by machine automatically. A census that once threatened to take the better part of a decade was completed in a fraction of that time. This is the moment the story quietly shifts. Until now, machines had been calculating numbers in, numbers out. Punched cards changed what a machine could be used for. A card could represent a person, a transaction, an instruction. The machine was no longer simply doing arithmetic. It was beginning to process information. The company Hollerith built to commercialize his tabulating machines would eventually become part of a much larger corporation that took the name International Business Machines, IBM. A name that would follow this story for the next century. But punched cards, for all their power, were still mechanical, still limited by moving metal parts that could only move so fast. And in the middle of the 20th century, under the pressure of a world at war, engineers would abandon gears entirely in favor of something far faster and far stranger: electricity moving through vacuum tubes. By the 1940s, calculation had become a matter of life and death. Military engineers needed to compute artillery firing tables, enormous sets of calculations predicting exactly how a shell would travel under different conditions. Done by hand or even with mechanical calculators, the work was agonizingly slow, and the war would not wait. The result was ENIAC, the Electronic Numerical Integrator and Computer, completed in the United States in 1945. It is often called the first computer, but that claim deserves a more careful telling. Other electronic and electromechanical computing machines existed before it, some developed in secrecy during the war. What made ENIAC historically significant was its role as one of the earliest general-purpose electronic computers, a machine that, unlike Babbage's mechanical vision, actually existed, actually worked, and could be reprogrammed to solve different kinds of problems. ENIAC filled an entire room. It weighed roughly 30 tons and relied on approximately 18,000 vacuum tubes, fragile glass components, each one capable of failing at any moment and knocking the whole machine offline. Technicians spent hours each day hunting down burnt-out tubes just to keep it running. And yet, despite its size and fragility, ENIAC could perform calculations thousands of times faster than any mechanical device before it. Think about that contrast. A machine that occupied an entire room, consumed enormous amounts of electricity, and required a small army of technicians to operate, performing calculations that a modern smartphone, sitting quietly in someone's pocket, could now complete in a fraction of a second, without anyone noticing at all. The leap from mechanical gears to electronic switching was not a small improvement. It was a fundamentally different way of computing, measured not in the movement of metal, but in the movement of electricity itself. And once that leap had been made, there was no going back. The only question left was how to make electronic computing practical enough for the world to actually use. Through the 1950s and into the 1960s, computers grew more powerful and more reliable, but they remained enormous, expensive, and firmly out of reach for ordinary people. These were the mainframes, massive systems housed in dedicated, climate-controlled rooms, tended by specialized staff, and owned almost exclusively by governments, universities, banks, and large corporations. A single mainframe could cost more than most people would earn in a lifetime. Access to computing power wasn't something an individual simply had. It was something an institution possessed and doled out, But something important was happening beneath the surface of these machines. Computers were no longer used only for scientific calculation or military purposes. Banks began using them to process transactions. Airlines began using them to manage reservations. Corporations began using them to track payroll, inventory, and volumes of business records that would have been unthinkable to manage by hand. Computing was quietly becoming infrastructure, an invisible layer running underneath modern civilization, even though almost no ordinary person had ever touched one or expected to. That was about to change, and the change would come from an unlikely place. Not a government lab, not a corporate research division, but a wave of hobbyists, engineers, and entrepreneurs who believed computing power shouldn't belong only to institutions. The barrier standing between mainframes and ordinary households was, more than anything, a matter of size and cost. The breakthrough that finally broke it was the microprocessor, an entire central processing unit shrunk down onto a single small chip of silicon. Where ENIAC had needed a room full of vacuum tubes just to perform basic arithmetic, a microprocessor by the 1970s could fit in the palm of a hand and perform calculations far faster, using a tiny fraction of the power. Suddenly, a computer small enough and cheap enough for an individual to own didn't sound impossible anymore. The change happened quickly once it started. Hobbyist computers like the Altair 8800 arrived as kits enthusiasts could assemble themselves, sparking a wave of grassroots excitement around personal computing. Companies like Apple, with machines such as the Apple II, began building computers designed for regular people rather than trained specialists. When IBM entered the personal computer market with its own machine, it signaled that this was no longer a hobbyist fad. Personal computing had arrived for good. For the first time, a question could be asked that had never made sense before. What happens when computing power stops being something you visit in a specialized room, controlled by specialized people, and becomes something you simply own? Millions of people were about to find out. But even as computers found their way into homes, schools, and offices, those machines were still, in a real sense, alone. Each one an island, holding its own data, disconnected from every other computer around it. The next revolution wasn't going to come from making computers faster or smaller or cheaper. It was going to come from connecting them. In the late 1960s, researchers funded by the United States government began experimenting with a radical idea. What if computers, instead of operating in isolation, could communicate directly with one another across long distances? The result was ARPANET, an early experimental network connecting a handful of research computers, a modest beginning that would eventually grow into the sprawling global internet we rely on today. There is an important distinction often blurred in casual conversation. The internet and the World Wide Web are not the same thing. The internet is the underlying network, the infrastructure that allows computers around the world to exchange data. The web, developed later by the British computer scientist Tim Berners-Lee, is a system built on top of that network. A way of organizing and linking documents so anyone could navigate between them with a click. The internet is the road. The web is what got built along it. Once that connective layer existed, everything computers had been used for began to change shape. Communication no longer required a landline. Commerce no longer required a storefront. Research no longer required a trip to a physical library. Entertainment, education, and social interaction all began flowing through this newly connected web of machines. The computer had stopped being merely a device that processed information in isolation. It had become a gateway, a single point of access to nearly everything humans had ever recorded. And yet, for a while longer, that gateway still lived on a desk, tethered by cables. That was about to change too. Through the final years of the 20th century and into the early 2000s, several technologies were evolving along parallel tracks: mobile telephones, digital cameras, satellite positioning systems, portable music players, and increasingly compact internet-connected computers. Then, in the mid-2000s, led by the arrival of devices like the iPhone and the wave of smartphones that followed, all of those separate technologies converged into a single pocket-sized device. A phone, a camera, a map, a music library, a web browser, a computer in the truest sense of the word fused into a slab of glass and metal that fit into a pocket. The implications went far beyond convenience. For the first time, a majority of the world's population carried a powerful, internet-connected computer with them at nearly all times. Communication became instantaneous and constant. Information became available on demand, anywhere, at any hour. The computer was no longer a destination you sat down in front of. It had become a constant companion, woven into the rhythm of everyday life. At this point, computing had already achieved something almost unimaginable to the merchant sliding beads across a wooden frame: machines fast enough, connected enough, and portable enough to reshape how billions of people communicated, worked, and lived. But one more transformation was still ahead, and this one wouldn't just change what computers could do for us. It would begin to change what tasks we thought only humans could do at all. The idea of a thinking machine did not appear suddenly in the 2020s. It had been a subject of serious research for decades, tracing back to the mid-20th century, when early computer scientists first began asking whether machines could be built to simulate aspects of human reasoning. For a long time, that research moved in fits and starts, held back by limited computing power, limited data, and limited algorithms. What changed in recent decades was a convergence of three forces: dramatically more powerful hardware, vastly larger quantities of digital data to learn from, and refined algorithms. Particularly a family of techniques known as machine learning, in which a system improves at a task by being exposed to examples rather than programmed with rigid rules. Within machine learning, an approach called deep learning, built around structures loosely inspired by networks of neurons, proved remarkably effective at recognizing patterns in enormous datasets. Patterns in images, sound, and language. Trained on staggering quantities of data, these systems became capable of a new category of task altogether, known as generative AI, producing new language, images, and code, rather than simply sorting or retrieving existing information. Today, systems built on these foundations can understand and generate human language, produce original images from a written description, transcribe and recognize speech, write and debug computer code, and assist with tasks that, until very recently, seemed to require a human mind sitting behind them. It is worth being precise here, rather than swept up in the drama of the moment. These systems are not conscious. They do not think or feel the way a human being does. What they do is perform extraordinarily sophisticated pattern recognition and generation, built on mathematics, trained on data, and running on hardware that traces its lineage directly back through mainframes, through ENIAC, through Babbage's unfinished analytical engine, all the way back to a frame of sliding beads. And that lineage brings us to the real question at the heart of this journey. The earliest counting tools were built to help humans count. Mechanical calculators were built to help humans compute. Programmable machines were built to help humans process. Networks were built to help humans connect. And now, machines are beginning to take on tasks once thought to belong exclusively to human intelligence. So what happens next, when the tools we built to extend our minds start reaching for the very edges of thought itself? Picture, once more, that ancient marketplace. A merchant sliding a single wooden bead from one side of a frame to the other, counting sacks of grain one at a time. Now picture a data center, humming quietly somewhere in the world at this very moment, performing more calculations in a second than that merchant could have completed in several lifetimes. Calculations that write sentences, recognize faces, and generate images that never existed until the instant they were asked for. The distance between those two images is almost impossible to comprehend, and yet trace the thread back, and it never actually breaks. The abacus led to the mechanical calculator. The mechanical calculator led to Babbage's impossible machine. Punched cards taught machines to process information instead of just numbers. Electronic switching made calculation blindingly fast. Mainframes turned computing into infrastructure. Microprocessors brought that infrastructure home. Networks connected every machine to every other. Smartphones put that connected world into a pocket. And now, artificial intelligence is asking machines to take on fragments of the work our own minds have always done alone. The bead frame never disappeared. It simply became the first link in a chain that never stopped growing. Where that chain goes next, none of us can say for certain. But if the last few thousand years have taught us anything, it's that the story is far from finished. If you enjoyed traveling through the evolution of computers with us, subscribe to Exhibit A, where we dig into the hidden histories behind the everyday objects and technologies all around you.